Hello, everyone, and welcome to the fifth week of the Cats for AI lectures. Today is a special week because we're starting with guest lectures, and we're very happy to introduce Pietro Vertechi. Pietro is an independent researcher and software developer who's been working on the intersection of category theory and machine learning, and he's going to be telling us today about neural network layers as parametric spans. So take it away, Pietro.
So, hello everyone. So thanks for the introduction. And yeah, today I'll talk about this project that I've been working on with my colleague, Mattia Bergomi. So first of all, a bit of a practical thing. I think we can keep this somewhat informal. So if you have doubts during the presentation, there are things that kind of make it hard for you to keep following, feel free to interrupt and to ask questions. So in terms of structure of the talk, I will start by giving some context about neural networks in general. I will describe the zoo of different linear neural network layers, and I will try to emphasize the commonalities among the different linear layers. Then I will attempt to give a general definition of what it means to be a linear layer, and I will use two key ingredients that I will introduce during the talk, which are Frobenius integration theory and parametric spans. And then I will show how one can interpret classical layers in the light of this general definition. And I will choose a few concrete examples. In particular, I will show dense layers, convolutional layers, and some typical layers from geometric deep learning. Kind of from a broad, kind of simplistic perspective, a neural network is just a stack of simple layers. So in this case, we are using convolutional layers, the pointwise nonlinearities with ReLU, and pooling layer. And we are stacking them, attempting to approximate a complex function. So in this scenario, we're trying to approximate the function that takes as input an RGB image and gives as output a list of probabilities. So the probability that the image is a lifeboat or a ladybug or a pizza, a bell pepper, an espresso mug, or whatnot. And this seems reasonably straightforward, but of course things are a bit more complicated because if we zoom in, we can see that each layer is actually quite complex on its own. So here I'm zooming in on the convolutional layer, and this is one of the most common layers when working with images. And the way in which it's working is that it's sliding a filter against a series, so actually several filters, each against all the regions of a bunch of images, and then it's computing all the results, suming them together and combining them to achieve an output. And this has a lot of interesting structure, but of course it's not the only layer that you could have used. Many alternatives exist. And in my opinion, this is one of the kind of the hardest thing to do in practice in deep learning. How would you choose what layers to use? And even if we restrict ourselves to linear layers, which I will do in these talks, I will not worry about non-linearities or non-linear poolings, but even only with the linear components, many options exist. So we have dense layers for unstructured data, so the basic perceptron-like thing. Then for images, we have planar convolution and transpose convolution. For more general group structures, there's group equivalent convolution, not to mention all the options that become available if you're working with more complex geometries, such as graphs and Riemannian structures in geometric deep learning. And of course, choosing a layer is also not enough, because each layer will come equipped with a set of hyperparameters that have to be manually tuned. And to me, this is actually overwhelming. So by training, I'm not a machine learning practitioner, and this has been a big stumbling block for me. How do you actually come up with an architecture that does its job? But from a more conceptual point of view, this leads to two very open-ended questions. So the question one, given that this plethora of linear layers exist, is what are the defining features of a linear layer? What is it that makes it that some operator is a linear layer? And question two is whether there is a global, well-behaved space of all linear layers. So can we come up with a kind of a big, smooth space such that the choice of a linear layer and hyperparameters is just a point in this space? This, of course, would have kind of huge practical implication, right? Because then it'd be much easier to define these layers. And I think it's helpful in terms of defining features to divide, basically split them into two categories: those that are general and those that depend on the domain. And I will start trying to list the general features. And the first one is obviously linearity, because we're working with linear layers. And a bit more precisely, what I mean by this is that, as you can see in this simple example, just a linear combination of the activation values, we want that the output is linear in the input. So it depends only linearly in the inputs, and it also depends linearly in the weights. So this concept in mathematics is called bilinearity. So basically, a function is separately linear in both arguments. And this is not enough, actually, because we will use our layer to compute some output, but then to this output we will associate an error by our loss function. Essentially, it's another key component of deep learning. And during training, we will want to backpropagate the error all the way to the input. And we will need also an operator that does that, which is essentially the dual of the neural net, of the layer. The terminology is not straightforward here. I like to think in terms of dual, because now by mathematics, when you flip the direction, it's by duality. So the dual of the output is mapped to the dual of the input. But you may have heard of this operator as adjoint, which also makes sense. If you have a dot product of these spaces, you can identify the dual with the space itself, or more simply backward pass. When you're just in practice implementing a layer, it will have a forward method and a backward method, which is just the dual. And we want this to exist, and we want this to be, again, a linear layer. So these are the general requirements: bilinearity and duality. And for this to be practical, we want that our linear layers are informed by the domain. And this, I think, can happen in one or two ways. The first thing that we should keep in mind is equivariance, which I think was a key factor in determining the success of the convolutional layer for images. For example, in this simple representation, we have an image here of a chess piece, a rook, and we apply, we convolve it with a filter, and we get this output. But we could have shifted the image and applied the convolution to the shifted input, or we could have convolved the image and shifted the output, and the result is the same. So this diagram commutes, and this is known as equivariance. It's a key component of linear layers, and is in general implemented with the so-called weight sharing. So if you think about the connection between one output pixel and one input pixel, the weight associated to that connection will only depend on the offset between these two pixels. So it will be a translational invariant, the weight that will be shared. And the second component is locality. So very often, the spaces that we're working with, they have some sort of a spatial structure, as could be the case, for example, for a 2D mesh embedded in a 3D space. It has a well-defined spatial structure, and it makes sense to ask that the inputs of a given output should be localized in space. So, for example, for some output, I only want to consider inputs in this region around the left ear of the bunny. And now that we have established both the general requirements of our linear layer and domain-specific requirement, the action plan becomes quite clear. So we want to give a kind of a general, broad, unifying definition of linear layer that respects bilinearity and duality, which will mean in practice that we get an easily computable backward pass. It incorporates the domain-specific requirements, which are local connectivity and equivariant constraints, which we will achieve by weight sharing. And that works on a variety of different spaces, both discrete and continuous, because that is the domain of deep learning. Sometimes you work on a discrete space, and sometimes you work on a smooth manifold. Now, achieving all of this is actually technically a bit challenging. And to do that, we will need to introduce two notions. So one is the notion of the Frobenius integration theory, which will formalize via category theory the interplay between function and measures, so which are dual to each other. And indeed, this will naturally lead to the notions of bilinearity and duality, and it's quite general, so it can be applied both to smooth manifolds in order for us to have continuous layers, or just to finite sets, more simply, to have discrete layers. And the second ingredient are parametric spans, which are a categorical diagram that we will use to formalize the notions of locality and weight sharing. And specific instances of parametric spans will recover classical linear neural network layers, both discrete and continuous. So let's start with Frobenius integration theory. Here, even though I mean, this talk is supposed to be at the interplay between category theory and deep learning, I will also have to introduce some notions from differential geometry. But if one is interested in geometric deep learning, there's no way around it. One just needs those notions. So I will start with a smooth manifold X. To form an intuition, you can just think about some smooth surface embedded in a 3D space, and I will denote f of x, the space of smooth real-valued functions on x. So basically, functions from this manifold x to the real numbers, and we ask that they are smooth. So they don't have any discontinuities, and they can be differentiated an arbitrary number of times. Then by m of x, we'll denote the space of smooth densities on x, which is basically things that can be integrated on a manifold, and it's the dual of it is in some sense the dual of a function, and it's just an object that has a well-defined integral. on our manifold X, and we will ask that they have compact support, that is to say that they vanish outside of the compact set, because in that way we will make sure that when we integrate them, these integrals always converges. So it's a technical requirement. And finally, we will use this notation to denote the integral on the whole manifold X. So this is the key data that we'll be working with. And this data is actually equipped with a fair amount of structure. So first of all, f of x is a commutative algebra. Now, for those who are not familiar with what an algebra is, it's simply a vector space, so I can have linear combinations on smooth functions, and this is again a smooth function. And it has an inner multiplication operator. So in this case, what one can do is to kind of pointwise multiply smooth functions, and you will get again a smooth function. And this is actually a bilinear operator. And similarly, m of x has also some structure. In particular, it is a module for the algebra f of x. And again, for those who are not familiar, it means that not only it is a vector space, so I can linearly combine smooth densities, but I can also multiply a smooth density by a smooth function, and I get again a smooth density. So this is what it means to be a module with respect to an algebra. I have this multiplication of an element of the module with an element of the algebra. And finally, the integral is simply a linear functional on m of x. So it takes as input a smooth density, and it yields a number, which is the integral of the density on the whole manifold. Now, this is the structure that you get when you look at one single space X, but in practice we'll be looked at several different spaces and maps between them. However, and this is important, not all maps will work. And in this slide, I will give basically the technical requirement for a map to be kind of well behaved for our purposes. I tried to use some kind of graphical representations to make this a bit less abstract. So this surface that I'm representing in wireframe mode is the space, the manifold X, and this line is the manifold Y, and the projection of the surface to the line is the map F. And we say that such a smooth map F from a manifold X to a manifold Y is a submersion if the differential is at every point surjective. So in practice, what needs to happen is that X is at least as high dimensional as Y, which works in this case, so it's dimension 2 versus 1. And at each point, the local approximation of this map, which will be basically a linear map from the plane to the line, is full rank, so it's surjective. And when that happens, we say that this map is a submersion. And kind of the key feature of submersions is that the fibers are well behaved. So this is a consequence of the inverse function theorem, that if we take a point P in Y, so in this case I'm highlighting here a little orange dot on this line, if I fix a dot here, then I can consider the fiber over this dot, which is essentially the pre-image according to this map F. So it's the subset of X that is mapped onto this point P. And now what the inverse function theorem says, thanks to the submersion assumptions, is that this subset here is not just a subset of X, it's actually a submanifold. And we see it in practice in this example. So we get a smooth curve embedded within a smooth surface. And as we vary the point P in the manifold Y, we see that this fiber also changes, kind of it moves around and potentially changes shape, but it always remains smooth. And this is very important for us because it gives us a way to transform a quantity on X into a quantity on Y, because now we are no longer forced to take the integral on the whole surface, but we can take the integral fiber by fiber, and instead of getting just a single value, we will get one value per each point of Y. So in terms of kind of machine learning terminology, this is some sort of linear pooling. So it's a fiber-wise linear pooling. We're just integrating fiber by fiber. And these are basically all the tools that we need to describe how functions and densities varies. And what we can show is that they are functors of opposite variance. Because if we have a smooth submersion from X to Y, this induces, first of all, an algebra homomorphism, F upper star from F of Y to F of X, which we call the function pullback, and it's given by precomposition. So if I have a real valued function on Y, and I want to pull it back to X, I just precompose with F. But we also get a linear map, F lower star, from M of X to M of Y, which we call the density push forward, and is given by the integration along the fibers of F that I've just discussed. And these two things are basically mean that F is a contravariant functors and M is a covariant functors. And but that's not all that we can say. They also respect some extra properties. So the first one is something that I like to call Frobenius reciprocity, because it reminds of the Frobenius reciprocity law in category theory. And what it says is that if I have basically a density on X and a function on Y, I can combine them in two ways. So I can first pull back the function, I multiply them on top, and I bring them down, or I can just bring back the density and I multiply on the bottom. And what Frobenius reciprocity states is that these two things should be equal. And the second law that should be respected is essentially Frobenius theorem. So what it says is that the global integral of some density mu can equivalently be expressed as the integral on Y of the fiber-wise integral on mu. So it's the same to integrate on the whole manifold or to integrate along fibers and then integrate on the base space. And if one combines these two formulas, you can prove that these operators are in some sense adjoints, in that the integral on X of F upper star Y times mu is the same as the integral on Y of Y times F lower star mu. So this is kind of I mean, the term adjoint is not quite accurate from the point of view of linear algebra, but it's accurate from the point of view of deep learning, because what this says in concrete terms is that F lower star and F upper star are the backward pass of the other. So if you write a neural network, and at some point you have F upper star as the forward pass, then F lower star will be the backward pass, and vice versa. So this naturally leads to writing architecture where it's very easy to compute the backward pass. So now I realize that all the structure that I've defined can be a bit overwhelming, but the plus side is that it can be described much more succinctly. So kind of all this structure that I've defined so far, so the function space, the density space, the algebra structure, the module structure, the pullback, the push forward, the various constraints, it can be succinctly described as a unique functor from sum, the category of smooth submanifolds and submergence, to gr of mod over R, where of course the basically the flip coin of the simplicity of this definition is that this category here, which I haven't yet defined, is actually quite complex. So I of course invite you to read the manuscript for extra details, but to get some intuitions, I will try to sketch the construction. And the key idea is that we start with a commutative algebra A, and from it we can construct a category mod A over R, which is the category of A modules equipped with a linear functional. And the intuition is that the algebra A are the smooth functions, the module are the smooth densities, and the linear functional is the integral. And these categories, they actually form a functor, mod over R, from the opposite of the category of commutative algebras to the category of categories. And as is always the case in these situations, we can glue all these categories together by means of the Grothendieck construction. So this is where the prefix gr, the term gr comes from Grothendieck. Now this construction is quite old. It's been around for a few decades, but it has had, I think, a revival in terms of application in recent years with this beautiful paper by David Spivak that I invite you to read, because it has a very, I think it's very clearly explained and shows very well the practical interest on this construction. In particular, it shows how the category of lenses is a particular example of this construction. So definitely a fascinating read. So now that we have established what this category is, we can basically just focus on the right-hand side and forget about smooth manifold and submersions, which are an important example, but all the relevant structure has been subsumed here. So we can say, and this will be our definition, that a functor from some arbitrary category C to gr of mod over R is a Frobenius integration theory on C. And we'll be interested in working with any category C that means a Frobenius integration theory. And indeed, there are several examples of this. So there's one example on smooth manifolds and submergence that we have developed in full detail. There's an example on measurable spaces and measurable functions that is detailed in the manuscript. But there's also a simpler discrete example on finite sets of functions, which I think could make for an interesting exercise. So how would one go about defining functions and densities for finite sets? So to sum it up, all this kind of big technical core of the paper, what we've seen so far is that the gradient deconstruction yields a global category, gray of mod over R, that axiomatizes the behavior of functions, densities, and integrals. And we've defined the Frobenius integration theory to be a functor from any arbitrary category to gray of mod over R. And we have seen that there is a natural Frobenius integration theory on the category of smooth manifolds and submergence, which of course we will use to define neural network layers on smooth spaces. And finally, the reason for doing all this is that Frobenius integration theories naturally lead to dualizable bilinear operators, which will be our neural network layers. So now that basically we have kind of established the technical framework to get general linear layers, we need to be able to adjust our layers to the domain, so to inject knowledge about the domain, in particular the locality and equivariance constraints we discussed. And to do so, we will use parametric spans. Now, first of all, a span, even without parameters, is just this categorical diagram. So it has three spaces, a space E of edges, a space X, which is the input, and a space Y, which is the output. And it has a map source from E to X, and a map target from E to Y. A parametric span is just the same, so it's a span, but we add a third leg that goes from the edges to the weights. And this will, the main purpose of this extra leg is to be able to come up to design some weighted graphs with weight sharing. Now, this is I realize that this is very abstract, so I will try to give some kind of visual some visual intuition of this. So we are starting with we're doing this in finite sets because it's going to be much easier to explain and to understand. And so E is this space here. So I represent this a few dots. These are input X. This is our output Y. And this is the space of weights. And I'm representing the values of the weights, which is color that vary on some predefined color scheme. And I've initialized them at random. Now, at the beginning, we define, of course, the source map from E to X and the target map from E to Y, and the pi map from E to W. And as soon as they connect, I can propagate the values of the weights all the way to E. And now when I update these values, as will happen during learning, they all update while staying locked in the E space. And after I'm done with the weights, for example, learning is finished, I forget about the space W, and I simply get a weighted graph where some values of the weights happen to be equal. So I think the key, just to go over it again a little bit more slowly, I think the key part that distinguishes this from a regular graph is that when we connect E to W, we can essentially pull back the values of the weights that we have here all the way to the edges, and then they stay locked, so that in practice I will only be learning a function over W, but it will be copied over. It will be copied over to E. And I said I would not notice the chat, but I did. And yes, there is a lot of similarity between this and possible alternative general formalizations of GNN. So I'd be extremely eager to discuss this in the future. So to recap what we've said about parametric spans, it's essentially a span which determines the connectivity together with a map pi from E to W that enforces some weight sharing. And if we furthermore assume that we are living in a category where we have a Frobenius integration theory, so we're in a category C, there's a Frobenius integration theory on C, and its parametric span is a diagram in C. So the objects E, X, W, Y are objects in C, and the arrows S, pi, and T are morphisms in C. Then, if that is the case, we can immediately obtain a linear layer just by means of a density mu on E. Because basically what we do, if we have our functions X and W on input and weights, we just pull them back. So S upper star X and pi upper star W, they both live in E. We multiply with the density mu. We get a density on E, and we push it forward to the output. And that's a linear layer, that's bilinear. And this is important from a practical point of view. It has a very easily computable backward pass, because to compute the dual of this thing, we take advantage of the duality between functions and densities, and all we have to do is permute the order of the legs of the parametric span, but it's the same computation. So to sum it up, the punchline for parametric spans is that they can be used to define linear layers with local connectivity, weight sharing, and a computable backward pass. So they tick all the boxes that we had said were the requirements for a linear layer. So in the final part of this talk, I'll try to basically apply it in practice and show how classical linear layers emerge as instances of this general construction. So this is by no means exhaustive, but I thought I would start with some kind of simple examples, and then in the future we can discuss more advanced layers. So we start first of all with the dense layer, so just a fully connected perceptron-like thing. So in practice, we are working on a discrete domain, just a bunch of points, and there is no symmetry, no structure whatsoever. Then the input will be a set with n of I points, the output a set with n of O points, and it's fully connected. So we have ni times no edges, and the weights are free to vary independently. So in practice, this map is trivial, is the identity. This is what happens when there's no structure, no symmetry. And so this is basically the parametric span that corresponds to matrix multiplication on a finite dimensional space. Now, convolutional layers are a much more interesting scenario, because here we have structure and we have symmetry. So in this example, we see that, well, the domain can be either discrete or continuous, because I mean you could discretize it to a grid or not, but you always have a symmetry, which is this translation. So we can see it clearly in the GIF, where the basically the red square is the output image, the blue square is the input image, and the shaded area is the filter. And we're moving it around to compute the various outputs. And here what we see is that of course the spaces are very easy to figure out. So the input space will just be some shape, Si of some rectangle. The output space, some shape SO, some other rectangle. And the weights space will be the shape of the filter F. And the edges, I will have as many edges as the kind of combination of a point in the output and the point in the filter space. And of course, these maps here on the right are just the projection. And this map on the left is actually the interesting one that tells me how to combine basically from a pixel in the output and a point in the filter, what is the corresponding pixel in the input. And this is basically the map where the hyperparameters of the convolutional layer live. So for example, this will be in general a linear combination of these two, and the coefficients will determine stride and dilation on the convolutional layer. But of course, they're kind of encapsulated together in a unique morphism in our category. I think there's a separate representation of a convolutional layer that stems from this framework, which makes actually more sense to me than the GIF that I showed you. And I think it's more amenable to continuous generalization. I'm doing it for 1D convolution, because otherwise it would be a nightmare to draw. And the idea is that, so 1D, it means that basically X is a line, Y is a line, and the filter W is again a line. And this is our input signal, this is the output we're gonna get, and this is basically the filter against which we're gonna convolve. And the edges basically are the pairs X and W that are gonna be connected. Of course, there's some irregularity at the boundary due to padding. We cannot go outside of the domain. And they are not only mapped to X and Y, but also to W via these basically these projections. And if we fix a point in Y, we can get the fiber, which is basically all of the edges that will be mapped to that point. And then this fiber can be projected both to X to see what are the inputs for that output, and to the filter W. And then as we move this point around in W, we can see that the fiber varies over E, and so does the projection of this fiber on X. Now the projection on W is actually a bit less interesting, because we always have access to the whole filter, except of course when we get close to the boundary. So the only activity you see on W is when you get to the boundary, that only some of it is used. So this, I think, is a kind of different way to visualize these things more interactively. And finally, the last use case is geometric deep learning, where basically it's no longer kind of a planar space, but kind of a more complex structure, for example, a mesh in a kind of a 2D mesh in a 3D space. And again, many layers exist, but here I think a very kind of very important paper for me in this field, what is Monti et al. Paper from 2017, where they kind of understood the overall structure of many of these layers. And basically what they came up with was actually not very different from a parametric span. So what they said is that you need some sort of neighborhood relationship on your mesh. So you say that this point has these neighbors, and then some local coordinates on this neighborhood. So here I'm showing polar coordinates rho and theta. And if you have this, you can create a parametric span as follows. So the input and the output are both this surface X. The edges are the pairs of neighbors. So QP, where P is a neighbor, is in the neighborhood of Q, and then mapping this pair to Q is the first arrow S. Mapping this pair to P is the arrow T, and our local coordinate that go to R to the power of D, which is the dimensionality of the manifold. Then this local coordinate actually form our weight sharing map pi. So we see that all the geometric layers that are within this classification by Monti et al., then they're also part of our framework. So that's everything I wanted to discuss today. So to sum up this last part of the talk about parametric spans, what we've seen is that we can use parametric spans to induce linear layers with local connectivity structures and with weight sharing constraints, and that this already has some practical advantages, this formalism, because the backward pass of these layers can simply be computed by permuting the legs of the parametric span, so by changing which leg we decide to be the output, essentially. And that parametric spans in the category of manifolds of submergence, which in practice will always be our primary example, encompass dense layers, convolutional layers, and variations thereof, and many geometric deep learning layers. And of course, it will be interesting to see if kind of very recent formalization that has been discussed are also part of this framework. And I think the kind of the upshot of this, which was a bit of a surprise to me, but I think it's a positive surprise, is that we can not only use category theory to see how kind of things are linked to each other, but we can actually use it for how layers are connected, but we can really use it at the macroscopical level to define the macrostructure of a single linear layer in categorical terms. And so this is where we are so far. But in the future, we plan to, so first of all, incorporate nonlinearities, because our limitation was a bit artificial to only work with linear layers, and to try and use the same formalism of the parametric span to encode a global linear architecture, so not just the single layer, but the whole network as a parametric span, which we're optimistic about, because traditionally, not just the single layer, but the whole network was a weighted graph. So we think the same should hold for parametric spans. And finally, I wanted to put this work in perspective within kind of a broader work that Mattia, Bergomi, and I have been doing in the past few years, where we have attempted to create kind of an overall framework for neural architectures with the following properties: modularity and composability on the one hand, and existence and computability of duals for reverse mode differentiation. So to make it a framework that is easy to implement on CPU and GPU in practice. And I think the big important step for us will be to combine the works that I'm studying here with this work on parametric span. And that's everything that I wanted to discuss today. Thanks a lot, everybody, for your attention.
Thank you, Pietro, for a thoroughly fascinating talk. We're going to do audience questions now. So if you have a question, feel free to ask it in the chat or raise your hand. While we collect audience questions, I'm going to ask a question of my own, which is, in the beginning, you mentioned that these layers are, so they're linear in both the inputs and the layers because we're, sorry, in the weights and the inputs, because we're talking about really one layer. My question is, when we add weight sharing inside that layer, don't we stop being linear in the weights due to the copying of the weights?
So I think it's probably a good slide for that. So no, the weight sharing actually works fine. And because basically, and the reason is essentially that this operator, so pi star that's pulling back, that's again linear. So we have no problems. But I think what your intuition is that very often, especially in the continuous case, we will not actually work with all functions on W, but we will parameterize some functions there. So basically, so what I'm trying to say is that we are linear in the weights in a very abstract sense. So the output is linear as a function of this W here, but in practice we will give W via some parameterizations of functions here, and that will no longer be necessarily linear. So it depends exactly how to choose to parameterize things. So for example, we could choose some tensor-based, well, but again, it depends. I think it's easy enough to keep it linear if we choose a basis of functions on W, and then we only take linear combinations on those. But that's a good point. I think one has to separate, and indeed in the Monti et al. Paper, they do that. They do a separate step where they say, okay, but now let's parameterize functions on our kind of local coordinate space. And there you could introduce some nonlinearities, that's true.
I see, thank you. It looks like Pim has a next question.
Yeah, I have two questions, if I may. Firstly, could you say that so pi needs to be like a submersion in one of your formulations, and it feels a bit counterintuitive to me. I feel like it would also make sense to, or maybe in general, can you comment a bit on the submersion property? In that I feel that like maybe if the edges are like a set of lines on the space or something, then it doesn't really feel like a submersion is the natural thing. It feels, or maybe I'm misinterpreting.
No, I think it's very interesting. And basically the key idea is that I think there are two answers to that. One, and I think, well, this is gonna get very technical. I hope I don't get everybody too lost, but the idea is that in many examples, for example, in all the example that I've seen from, for example, your papers or the papers with Taco Cohen on the basically how to generalize convolutions, arbitrary groups, and surfaces. This map from E to Y is actually a product projection, because basically for every point on the output, you have the whole of W on top of it. So basically, so basically, our space E is a space that you never mention explicitly, but that you would only see as a product of the output space and on the integration space. So for group convolution, this would be G times G. and for gauge convolution, this would be x times r to the power of d.
Yeah, or the tangent bundle.
Exactly. So this is always, but the reason why, the thing I don't like about that framework is that unfortunately, it's not closed by duals, because the transpose of that layer, then it's no longer a product, is mapped here, not necessarily. Instead, if we weaken the assumption to submersion instead of product projection, then I think we gain that kind of all the combinations work and we never leave the framework. So basically,
are you saying that it doesn't work if you take a tangent plane as E, or that your framework, like what breaks down? I'm curious. Maybe we're going too deep into the details.
Maybe it's too deep, but what I think breaks down a bit in the, for example, in the gauge equivalent convolution, is that it's not immediately clear to me that the gauge equivariant transpose convolution is again like the structure becomes asymmetric if I force E to be W times Y.
Interesting. Maybe we should talk about this offline.
Let's take it online. But I agree that technically you only need T to be a submersion to integrate along fibers. And these, they don't really need to be submerged for the forward pass, provided that you can figure out how to do the backward pass yourself. So you only need all of them so that you have basically both the value and the derivatives. But yeah, let's not go too deep into this, but I'd be curious to keep discussing with you, because I think the interaction is very promising.
Yeah, I have another question, but maybe I'll ask that after other people have asked, if they have any.
So there seems to be a raised hand from Andrew.
Yeah. First, thank you for this talk. It's a lot to think about. Maybe I just missed this little detail, but we have here that a parametric span induces this map, and so we have an input function, but then we end up getting an output measure. So how does it work that we convert that back into a function so that we can actually do this multiple times?
Yeah, that's a good question. I dodged it a bit here, but it's a very good point. And the idea is that basically, if you wanted to get a function on the output, instead of a measure on E, you would have needed a measure on the fibers, because then you do the fiber integration. But in practice, what I believe is the more practical way to go about this is that then you also have a strictly positive density on Y, and then I divide by that density. So I think that's how you would do. So in practice, if you really want to do kind of a network and change these things, basically every space will have its own density. So I pull back the function here, I multiply by the density of this space, I push forward, and I divide by the density of this space here. So I think, but your intuition is fully correct. You also need a non-zero density to divide and get back a function.
Great, thank you.
Thank you. And it seems we're over time, but let's take one more question from Yeva, Jules, Zanzi, and or Matteo.
It's Matteo here. This is the head speaking now. Thanks very much for the talk, Pietro. It was very, very interesting. And I know we're going over time, so maybe keep this as short as you can, but I'm really intrigued by this claim that you can compute a backward pass by permuting the legs. What do you mean exactly by this?
So basically, what happened, and I think I also, I mean, I apologize, I think I also went over time. I wasn't planning to take this long for the talk, but then I kept adding interesting kind of examples and visualizations, and then I went completely overboard. But the idea, I think the key trick, and I think we're in exactly the right slide for that, is that this thing that I was saying before, that S upper star and S lower star are adjoint one to the other. So basically, let's imagine I wanna compute the backward pass of this with respect to the input. I will also have to do with respect to the parameters, but I start with the input. Then the weights are fixed, and I need to start with the dual of the output, so with the function on y. So I start with fy times fw, and I will end up in the dual of the input. So m of x. And this will just be the same formula where I've exchanged t and s, and x has been replaced with y. So to compute in practice, to compute the dual, I would pull back this function. I would have a function here, which are the weights that I fixed. A function here, which is the dual. A function, because a function lives in the dual of the measures. I pull them both back, multiply them, multiply with the measure, and push forward, and get the measure in x, which is the dual of the input. So, so in practice, I think this, and but by all means, in the manuscript, this is discussed much more thoroughly. So I invite you to see there the details. But this is kind of a conceptualization of why, in my opinion, basically we get that the dual of matrix multiplication, you always get matrix transpose, but also the dual of convolution, you get conv transpose, which has a very similar structure. I think the key notion is this parametric span here. But there's a kind of there really is a section on this in the manuscript, so definitely go for it. But it's a practical thing. Like I have a work in progress implementation, and you can manually say in the backward pass just call the same as the forward, but with different arguments, and I test that the derivative is correct, and it does work. It's very practical, I think.
All right, thank you very much.
Thank you very much, Pietro, for a wonderful talk and all the questions. We're going to end it here, and I would just like to invite you and remind you that next week we're going to have our guest lecture number 2 from Taco Cohen regarding causality for deep learning. So thank you all, and see you next week.
Thanks, Pietro. It was a lot of fun.